In the last lecture, we introduced the concept of magnification, because the image of an object formed by a mirror is not always the same as that of the object. We also found that if an object is very close to a concave mirror, then its size increases manifold, and therefore, these concave mirrors are used, for example, by dentists to examine the teeth of their patients. And then we also learned the formation of images by convex mirrors, and we derived the mirror formula, which is exactly the same as that for a concave mirror. Then we explained the concept of field of view and explained why convex mirrors are used as side mirrors in cars, buses, trucks and scooters. Today, we continue with the discussion. I will show you first of all this slide, which shows the relation between V and U by a concave mirror. As you know, the distance of the object from the mirror, and V is the distance of the image from the mirror. And you can see that this is for a concave mirror of focal length 25 centimeters. And you can see, as long as U is such that the object is away from the focus, then V is always negative. That means, the image is always real. When U is less than the focal length, the distance of the object is less than the focal length, that is, the object is nearer to the mirror than the focal length, then V becomes positive, showing that then the image is virtual. Let us try a few examples. A man is shaving with his face only 15 centimeters from a concave mirror. If you have seen your father or elder brother shaving, you would see that if he has a concave mirror, he places like this to see the hair of his beard. So, it is 15 centimeters. If he obtains an upright image with a magnification of 4.0, what is the focal length of the mirror? So, we must first of all see what is given, and what is given in this case is the distance of the object, that is U, and we know for a concave mirror the distance of the object is negative. So, U is minus 15 centimeters. M, as we have already learned for a concave mirror, the magnification is minus V by U, and in this case it is 4.0. So, from this equation we can find V equal to 60 centimeters. So, we have now V and we have now U. So, we use the mirror formula 1 by V plus 1 by U is equal to 1 by F and get F, and F turns out to be minus 20 centimeters. Again correct, because the focal length of a concave mirror is negative according to our convention. You remember the convention, we are using Cartesian convention. The light comes from the left and all distances measured to the left are positive, all distances measured to the right are negative, all distances measured upward from the axis are positive, all distances measured downward from the axis of the mirror are negative. So, this is the convention that we are using, and this is the formation of image when the distance of the object from the mirror is less than that of the focal length. And you can see what is happening. This is the object, this red one, and we have a ray from the center of curvature which should go undeviated. So, that is the ray. Then we have a ray which falls on the mirror at P and gets reflected according to the laws of reflection, and then we have these two rays, and these two rays you can see they are converging and they appear to meet at the point I. So, I is the image of O. So, you can see that this image is formed behind the mirror. It is a virtual image, it is erect and magnified. Let us take another example. Prove that the image size is always smaller than the object size in a convex mirror for a real object in front of the mirror. Now, since the object is in front of the mirror, U is obviously negative according to our convention. For a convex mirror, you remember that F is on this side, it is towards the right of the mirror, and therefore, it is positive. So, the image distance v is found to be 1 by v plus 1 by u equal to 1 by f. We are given u, and therefore, we can write down this equation. Therefore, 1 by v plus 1 by u plus, since u is negative, this becomes negative sign, and the other side it becomes positive sign. So, we have 1 by v equal to 1 by u plus 1 by f. We can write v equal to u f by u plus f. And now, you see that the denominator is always larger than the numerator, whatever the value of u, and therefore, the size of the image is always smaller than the size of the object. So, in a convex mirror, size of the image is always smaller than the size of the object. Let us take another example. Here we have a concave mirror, and we have an object placed at 2f, that is at the center of curvature, and a plane mirror is placed at the focal point. So, what happens? A ray goes from here, and if the mirror is not there, the image is formed here. You remember that if the object is at 2f, the image is also at 2f. It is inverted, and it is of the same size as the object. So, if this mirror were not there, this would be the image. And now, since the mirror is there, this image acts as the virtual object for the mirror, and its image is therefore formed 20 centimeters in front of the mirror. You can also go through the analysis. You can assume that the plane mirror is a spherical mirror of radius of curvature infinity, and you can do the analysis again. But physically, the result is simple. You have got an object here. If the mirror is not there, then the image is formed here. This image acts as virtual object for the mirror, and therefore, image is as much behind the mirror as the object is in front of it. Therefore, final image is formed here. Let us take another example. The diameter of the sun subtends an angle of 32 minutes at any point on the earth. What should be the size of its image formed by a concave mirror of radius of curvature 200 centimeters? Let me show you the figure first. Here is a concave mirror, radius of curvature is 200 centimeters, and these are the rays coming from the sun. They are not parallel, they are at an angle of 32 minutes, which is very small angle. Actually, it has been exaggerated too much. Actually, they would be almost parallel. The angle between them is only 32 minutes, that is half a degree. And since they are almost parallel, the image is formed at f, and this is the size of the image. And since this is 32 minutes, this angle, half of angle is 16 minutes, this angle is also 16 minutes, and I is this times the angle 16 minutes, because the angle is very small. So, we can take 100 centimeters into 16 minutes. So, you can find what the distance would be. The distance is 100 centimeters, 16 minutes. Therefore, I dash f, and the total image is twice that. So, I dash f is 100 times 10 16 minutes. So, angle is so small that you can take 10 to be equal to the angle. So, 100 into 16 minutes. So, you find this is 0.047 centimeters. Therefore, the total image is twice that, 0.094 centimeter. See, geometry is very simple. This angle is 32 degrees, therefore, this angle is also 32 degrees, and we can find this easily. Another example, an image produced by a convex mirror of focal length f is 1/pth the size of the object. What would be the distance of the object from the mirror? What is given? The image is virtual. The image produced by a convex mirror of focal length f is 1/pth of the size of the image object. The image is virtual and erect in a convex mirror, always. We have done that so many times, that the image in a convex mirror is always virtual and erect. So, therefore, v by u in this case is positive, that is magnification is positive, because the image is erect, it is in the same direction as the object. So, therefore, v by u, the magnification is 1 by p, or 1 by v is p by u, and now we have 1 by v plus 1 by u. So, p by u plus 1 by u is equal to 1 by f, and you can find from this that u is p minus 1 into f. So, remember that in a convex mirror the image is always smaller than the object, it is virtual and erect. Now, having done mirrors, I think we are going now towards lenses, and the first thing is to see how the rays get refracted at a surface between the two media of refractive indices mu 1 and mu 2. So, we have this of medium of index mu 2, this medium surrounding it of index mu 1, and this MOXN is the spherical surface. So, that is what we are going to consider, and if this angle is I, then this angle, this gets refracted, this is normal from C. So, this gets refracted and this angle is R. So, we make use of these things. In keeping with our earlier definition, we define focal point or focus the point where rays parallel to the axis either meet or appear to meet. So, that definition stays for all time, and we are using small angles. So, that sin theta can be approximated to the n theta and can be further approximated to the angle itself. So, let us go back to the same figure. So, MOXN is the surface, this angle is the angle of incidence, this red is the incident ray, and this blue is the normal line drawn from the center of curvature. This angle of incidence, this angle of refraction, and this angle is theta. This is, since this is parallel to the axis, we assume that it will meet at the focal point. So, f is the focal point of for this surface, and you can write now angle I is equal to theta plus r. This angle is equal to this angle, corresponding angles, and is equal to theta plus r. So, theta plus r, and moreover I times r, assuming that these are small angles, I times r, this is equal to theta times f, because this distance is I times this distance or theta times this distance. So, I times r is theta into f. So, we have got these equations, and the following expression, if we use the magnification, f is equal to I r by theta, I r by theta is I minus r, and I minus r is mu 1 by mu 2 times I according to the laws of refraction, and therefore, ultimately we get mu 2 r divided by mu 2 minus mu 1. And to remind you that we are using this convention, I have again in this figure. Light is coming from the left, all distances measured in the direction opposite to the light are negative, all distances in this direction are positive, all distances upward are positive, all distances downwards are negative. Now, the use of the above convention shows that for the convex surface to the medium mu 1, this is a convex surface, and for this we can see f is positive, f is in the direction of the light, therefore, this is positive. So, convex surface r is positive, and therefore, f is also positive. So, f is I r by theta. So, it remains the same mu r by mu 2 minus mu 1. So, there is no change in the equation, this one, mu 2 r by mu 2 minus mu, because r and f have the same sign, therefore, there is no change. It is a simple matter to show that the expression for f remains the same even when the surface facing the first medium is concave. So, let us now have a surface which is concave to this medium mu 1, and this ray comes, gets refracted, and it appears to come from this point f. Therefore, f is the focal point for this surface, and distance is negative because it is measured in the direction opposite to light. This is also negative because this is again measured in the direction opposite to light, and extend this ray backwards, then this angle is r and this angle is I, alternating angle, and I is equal to theta plus r, and this Snell's law is of course mu 1 times I is equal to mu 2 times r. You remember that we are taking small angles, so that sines of the angles are equal to the angles themselves. So, mu 1 I equal to mu 2 r, I equal to theta plus r, and this distance is I times r, or it is theta times f. So, I times r is equal to theta times f. We have these equations, and from these equations you can easily see we get f equal to mu 2 r by mu 2 minus mu 1 as before. In this case, the concave surface r is negative according to our convention, right, and so is f. So, I and r and f both are negative. So, again the sign has no effect on this equation. So, we again get f equal to mu 2 r divided by mu 2 minus mu 1, as we got in the case of the convex surface. So, whether the surface is concave towards the medium mu 1 or convex towards the medium mu 1, the relation between f and r is f equal to mu 2 r by mu 2 minus mu 1. We now get the relationship between the object distance u and the image distance v. See, in the case of mirror also we got 1 by v plus 1 by u equal to 1 by f. Let us see what kind of relationship we get in this case. So, again we take the convex surface towards the medium mu 1, and again this structure is the same. There is a object here and a ray goes like this with the angle of incidence I, because this is the normal, and gets refracted, and this is the angle of refraction, and this meets the surface at point I. Therefore, I is the image of O. C is the center of curvature. This distance is therefore r. This angle is theta, this angle is phi, this angle is alpha, and these angles are small. Let me remind you again and again, so that their sines and tangents can be equal to their magnitude. So, mu 1 I equal to mu 2 r, Snell's law. I is phi plus alpha. So, mu 1 into phi plus alpha, r is phi minus theta, because phi is equal to r plus theta. Therefore, r is equal to phi minus theta. So, phi minus theta, and then I rearrange terms and substituting the angles in terms of distances. Remember that the angle alpha is 1 by u, angle theta is 1 by v, angle phi is proportional to 1 by r, small angle approximation, and so we get this relation. And in terms of the Cartesian convention, as I said, this is positive and the image distance is positive. So, r and v are positive, u is negative, therefore, this becomes mu 2 by v minus now mu 1 by u into mu 2 minus mu 1 by r. So, this is the relation that we get between object distance and image distance. Now, this is a concave surface and we shall get the same relation. So, mu 1 I equal to mu 2 r, mu 1 from this geometry I is phi minus alpha and r is phi minus theta, and therefore, rearrange terms and you get mu 2 by v minus mu 1 by u equal to this. And now, we shall make use of the convention, and we see v is negative, u is negative, r is negative. So, all quantities are negative. So, it makes no effect on this equation, and therefore, this relation remains the same, and this relation is the same as for a convex surface. So, you notice that the nature of refracting surface has no effect on the relation connecting u, v and r. Remember too that this result is valid only for paraxial rays, rays making small angles with the principal axis. The procedure for ray tracing again remains the same. We have this object, this is a ray parallel to the axis, and therefore, this must go through the focus. This ray connecting this tip with C will go undeviated, because this is normal to this surface. So, this goes undeviated. So, you draw these two rays, wherever they meet or appear to meet is the point where image is formed. So, the procedure remains the same. And in the case of concave surface, again the procedure is the same. So, this ray is parallel, this will appear to come from the focus, this ray through C is undeviated and both of them intersect at I. Therefore, I is the image of point O, and therefore, this blue thing is the image of this red object. and you can see that this is much smaller in size than this, and it is virtual and erect. So, when the surface is concave, the image is virtual and erect and smaller in size. And now, having done the refraction at a convex surface and at a concave surface, we are in a position to take two such surfaces, either both like this or both like this or a combination of these. And these, where an object which has both surfaces like this is known as a lens, either like this or like this, either both convex or both concave, or one plane, one concave, one plane, one convex. All these are called lenses. And the basic types of lenses are, as I said, double convex lens. Both these surfaces are convex. Double concave lens, both these surfaces are concave. Remember that the refractive index of the medium inside these surfaces is higher than the medium outside, right. So, different from that outside, it may be higher or lower, but it is, if these are lenses, then it will be higher. Okay. So, this double convex lens, double concave lens, plano convex and plano concave, one surface plane, one concave. In the next lecture, we will continue with the same discussion and will define quantities related to lenses. And what are these quantities? These are principal axis, optical center, focal point, focal plane, etc., which some of these have the same connotation as they have for the mirrors. And we shall also see how the images are formed when there is a refraction at two spherical surfaces. And we shall also derive lens maker's formula for the focal length of a convex or a concave lens. And we shall see, we will draw a lot of ray diagrams to show how images are formed by lenses.